Hello everybody, this is clip video number 8 of our chapter 3, but this one is a new concept of this chapter 3. It is called the vector functions and the space curves. Okay, so previously what we did is the equation of the line and the equation of the plane, which is the three-dimensional object, okay, living in three-dimensional space. So today we are going to look at it as a functions, okay, and not only the straight line that we are going to study, but also the curve in a three-dimensional space as well. Okay, the word function actually you have learned in calculus 1, but in calculus 1 usually the function is coming from your r to r, or sometimes it's called the real value function. And for this one in your calculus 2, you are going to look at the function from r to usually r2 or sometime r3. Okay, depends on the context of the problem. All right, and r2 is a two-dimensional space, and the r3 is a three-dimensional space, which is the space containing vectors. Okay, so this means that right now your function, instead of using the f, usually we use the r t. So the domain contain only a single variable t, but then the output or the range consists of at least not at least, sorry, at most 3 components. Okay, depends on whether you are in 2-dimensional or 3-dimensional. All right, so it will be something like this. So let's go ahead and study what we have. So of course, because of the function, okay, then that is the so-called domain or the input. Okay, the vector value function or vector function, it is a map from the set of real numbers, as I told you, okay, to a set of vectors. Okay, so in math we write it this way. We use r. It is from r to r2 or r3. Okay, depends on how many dimension that we talking about. And so this means that this is the input, and the output consists of 3 components like this, or fti, gtj, and htk, and each of the component depends on the same input t. Okay, it is the same input t. So a domain of a vector function is defined as the intersection of all domains of its components, because as one value t insert in each of the component, you need to be able to evaluate each one of them. So it need to be the intersection, so that you don't left some of the component behind. Okay, and the other thing is that if you want to find the limit, this is very easy. So the limit of the vector function r, it is a limit of each of the component. Okay, distribute like that. So the limit of the function r exists if and only if each of the component limit exists. Okay, so that will be pretty easy and like straightforward. Okay, so what does this mean? It means that the limit question in this chapter becomes 3 limit problems in calculus 1. You know what I say? Okay, so just the limit of f, limit of g, and limit of h. Okay, so let's see. Can you determine the domain of this function? So look at the first one. What will be the condition on the square root of the first one? So your t plus 1, the one inside the square root, must be non-negative. So it means that your t must be greater or equals to -1. However, for the second one, the one inside the logarithm must be strictly positive, right? So it means that your t must be less than 4. So if you need to, and the last one has no condition, right, because it is a constant. So you can draw a diagram. This one is for the first term, and this one is for the second term, must be less than 4. So to look at the intersection, then here is the intersection between two of them, right? So it is from -1 to 4, like this. Thus, the domain of this function, vector function R, becomes close -1 to open 4. Okay, just like that, very easy. Okay, just look at each one of them. So now, look at the limit of this function as your t goes to 4. Okay, as your t goes to 4. So as we told you before, that the limit of the vector function is actually the limit of each of the component. Okay, if each of the component the limit exists. So let us look at it separately. The first one, as your t goes to 4 of e raised to power t minus 4, this is pretty easy, right? So it is a 1. How about your second one? Do you still remember this kind of limit? Oh, this is 2 over t minus 4. Okay, just one small thing that don't forget that this one and this one, they are different. Okay, so here it means that you got your sine of t minus 4 square. Okay, you got 2 of the sine, but this one, it means that you have your angle square. Okay, so this one, it is your angle square. Okay, but you got only one of the sine. Okay, and the other thing that you may need to recall yourself is that as your theta goes to 0, your sine theta over theta equals to 1. Okay, so it has to be the same order of the angle in order to make your sine theta over theta goes to 1. But this one, you got the order of 2. This one, you have the order of 1, okay, at the bottom. So you really need to change it to be the same. So you are going to multiply it by t minus 4 over t minus 4. Okay, so that the limit becomes sine of t minus 4 square over t minus 4 square, and the extra term of t minus 4. Okay, and this limit goes to 1. However, the second limit goes to 0. So at the end, the limit of the second term goes to 0. How about the last term? I mean, the last term seems to be troublesome, because this one, you got your absolute value. But look at this one carefully. Okay, look at the one on the top carefully. The t squared minus 8t plus 16. Actually, it is something that you are familiar with. It is t minus 4 square, right? And one of the properties that you may need to recall is that if you got this one square, is the same as you have your absolute value square. Okay, so this one is the limit as your t goes to 4 of t minus 4 square over t minus 4 with the absolute value. So it means that you can just go ahead and cancel, and you have limit t goes to 4 of the absolute value of t minus 4. Okay, so actually you may say that, hey, we need to think of the left hand side limit and the right hand side limit. Yes, it is actually, but because right now you got only one term, either left hand side or right hand side, as your t goes to 4, it becomes a 0. So this means that the limit of your last term is also 0. Okay, so this means that as your t goes to 4, your RT goes to 1, 0, 0. So that will be your limit, okay? Or you can write that the limit as your t goes to 4 of RT, actually it is 1, 0, 0. So it is basically each component limit, okay? Next, of course, as you have the limit, then you can determine the continuity, okay? So the vector r, it is continuous at the point A, okay? So the point A is one of the point in the domain, so this one is a real number, okay? So it will continuous if, of course, straightforward, right? That the limit as your t goes to A of the vector RT equals to the value, okay, of that vector when you evaluate your t at A, okay? So this is pretty straightforward as it is. Next, we are going to look at each of the problem, okay, so that you get familiar with the vector function. So look at the first one. Do you kind of familiar with, okay? Can you describe this curve, okay? Even though it's a curve, sometimes the curve can be really curve, or it can be a straight line as well. So for this one, actually the first component, usually we use the x as a first component, right? Because this one, finally will be the vector in R3. So the vector in R3 can represent by x, y, z as well. So your x is t, your y is 1 minus t, and your z is 2 plus 3t. So what does this mean? Actually, this r is a straight line, right? Because here is the equation of the line that is passing through which point? And it's passing through 0. You see 0 over here, okay, and 1 and 2, and parallel to which one? Well, what will be your directional vector? So it is the one again in front of your t in each of the component, right? So it is 1, -1, and 3, okay? So it's simply a straight line, okay? Simply a straight line, all right? What if you need to sketch the curve that has the vector equation like this? This one is a traditional curve that you really need to know, okay? Let us look at only this one first. So what should I say? Problem 2.1 first. If your RT contain only two component, cosine and sine, okay, cosine and sine. So can you make a guess? Because this is your x, this is your y. What is the relation between this x and y? Okay, the common relation that you should know is that both of them, x squared and y squared together added equals to 1. So it means that each and every curve, okay, will be the point on the circle, okay? Actually, you may say that, hey, like one of them should be a vector like this, okay? Yes, of course, it is a vector like that, but what we represent is just the trajectory of the terminal point of each vector, okay, when your t change, all right? So it will be something like this one, okay, along this circle, all right? So we are not going to write it as a vector like that, only the terminate point that we are going to interest, okay? So this one look like a circle, okay, in 2 dimension. Of course, you need to say that your t can be in 0 and 2 pi. So it will be a complete circle, right? Starting from here and then just going this way until you reach this point. If, I mean, actually your t can be any other. For example, it can be 0 to 4 pi. So what does this mean? So it's going to be travel along this circle twice, right? Twice. But still, all the trajectory look like this red circle, but you do it twice, okay? Okay. So let us go to this original problem. So your r, it is equals to cosine, sine, and then t, okay? So this sine and cosine will generate something like a circle, but your t will elevate each circle. Okay, for example, if you talk about the circle of, you know, two round like this, so you got two circle on each other, right? This is the one circle, and this is the second circle on top of each other like this. But if you add this term t, then each of the t that's changed, your circle will elevate up as it travel along the unit circle. Okay, it will elevate up. So it will look like, I think you guys can make a guess already. Okay, so here is a unit circle on the floor. However, because of this term, it's not going to be a unit circle on the floor, but it's going to be start from this one, and then it is going upward, okay, as a helix like this. Okay, but if you collapse this helix down, it will be the unit circle as well. You know what I say? Okay, so it's going to be the helix like this because of this t. Okay, and let's say that if your t is from 0 to like 6 pi, then it's going to be the triple helix, right? Because of this one. Okay, so this one is like a common curve that you should know. And sometimes we are going to determine the direction as well, that here's the direction of the helix. Okay, something like this, depends on each of the t that's travel, okay, along the curve. All right, so now we go back to some of the problem. Okay, for example, if you look at this problem again, you are going to find the domain. So do we have any this one, sorry, the comma is right here. Do we have any condition on t square? So your t can be any real number. How about this one? Your t minus 1 must be non-negative. So your t must be greater or equals to 1. And on the same time, your 5 minus t must be non-negative. So your t will be less than or equals to 5. So as we told you that we are going to do a intersection, right, among all these. I mean, for this one you don't need to draw it, right? You just look at the intersection between that two. That will be good enough, and the answer will be from 1 to 5. So the domain of your R, it is simply from 1 to 5. Okay, how about this one? I mean, this will be a mixed example already among what we have learned. Okay, look at this one. If you want to find the limit, okay, and this is a limit as your t goes to 0 from the right, so it has nothing for the first term, right? Because you can just plug in, so you got 1. For your second term, you again can simply plug in, so you got 0. But for your last term, okay, the L'Hopital's will come to haunt you, because this one is a 0 multiply negative infinity. Okay, so it is the indeterminate form. So what you need to do is to change this one into the fraction. So remember, and then you can use the L'Hopital. So at this moment we use the L'Hopital. So you got the limit as your t goes to 0 of 1 over t over negative 1 over t squared. So you find a derivative of the top separate from the derivative at the bottom. So you calculate again, and it end up with negative t. Okay, you do the reciprocal, so you got negative t, and your t goes to 0, so it is a 0 again. So this means that this limit equals 1, 0, 0. Okay, how about this one? Your t goes to infinity. The first one, the arctangent, you need to know this curve. Okay, so the curve of arctangent look like this, and this one is pi over 2, this one is negative pi over 2. So it means that as your x, or as your t goes to infinity, your arctangent will go close to pi over 2. Okay, this one is something that you really need to know from your high school. So the arctangent of infinity is pi over 2, but the e to the negative 2t, it is 1 over e, right? As your t goes to infinity, so it's go to 0. And the last one, it is a log of t over t. Again, it is the indeterminate form of infinity over infinity. So we can go ahead and use the L'Hopital to got the limit as your t goes to infinity of the derivative of the top over the derivative of the bottom. So again, as your t goes to infinity, this will be less and less, so it goes to 0. So this limit of your arctangent of your e and the log of t over t becomes pi over 2, 0, 0. Okay, so as I told you that one problem about the limit here will be 3 questions about the limit in your calculus 1. Okay, so we are going to stop this video clip right here, and then we'll continue. Of course, I mean, we already find the domain and the limit of the function, right, of the vector function. So what else that we usually interest when you talk about function? Of course, the derivative and the integration. Is it? So next time we are going to talk about the derivative of the vector function and the integration of the vector function. We'll see you then. Bye bye.